I think let's start. It's already 16, 18:10.
Okay, sir.
Hi everyone. So
Yes.
myself Javed Ahmad Dar. I am a PhD student at IIT Kanpur. So for this course, I will be handling the tutorial sections. We will be having a usual meeting on the Mondays from 6 to 8. Uh, I would first like you people to introduce one by one, so I get to know you people. Yeah, Arv, you can start.
And sir, this is Yavi. I am one of the faculty actually. I am not a student.
Okay,
I am interested in normally most of the civil engineering subjects to update knowledge
so you are faculty at?
in Hyderabad.
Okay.
Therefore, I joined the course,
Okay.
and actually I am geotechnical man.
Okay, okay. So you have done your PhD in geotechnical field.
No, no, so only masters. Long back, it was long
Oh,
back. I am a senior
oh,
faculty.
okay, okay,
So it is relevant for my subject. That's why I used to update some knowledge on this.
okay. Thank you
I
for
have basic
joining.
knowledge, but still I want to update.
Okay, okay. So yeah, Ria, Ria,
So,
can you please introduce yourself? Ria, am I audible to you? Uh, so someone has joined with the name S. Can you please introduce yourself? Okay. So let's start. I think they have just joined the meeting. They're not much interested. So last week the video lectures have been uploaded by the professor, and you people have went through those lectures. So it's just basic hydrology, water cycle, and its importance in our day-to-day life. So I will just first try to give the recap of what we have learned in those lectures. So is it better to go with the English, or should I change the language?
yeah, English is fine, sir.
Okay.
Sir, I would like to interact here a small question before you are starting.
Yeah.
If you give your area of working, so that we can
Okay.
also little bit learn
Okay.
more in that area. If
Okay.
relevant topic is coming, I will ask some questions.
Okay. Okay. So I work in the field of hydrology only, but my topic covers the heat waves. So
Okay.
basically, we try to understand how the extreme temperatures occur and what is the real drivers and mechanisms of these heat waves. And once we identify those mechanisms and drivers, we try to predict them based on those drivers. So heat waves
Okay.
is one of the common, I think, hydroclimatic extremes that we see every day, which are defined by when the temperature goes above some threshold. My particular research focuses on India only. I study heat waves in India only.
Okay, sir.
Hmm. So you have
Okay, sir.
you gone through bit through the hydroclimatic extremes earlier?
No, only BTech level only I have studied, not further.
Okay. So I'll start with the water cycle. Everyone will be having an idea of this. So hydrology is actually starts with us how this water moves from one uh, phenomena to another phenomena. So this all has been covered in your video lectures, but I will try to get a recap of this so that we can start with the questions and other discussions. And if you have any questions, you are free to ask at any time. So, so water cycle includes different components. So it starts with the land, the movement of water from the land to atmosphere and back to land. So it composes of different processes. So one of the basic processes, I think I have few I will note down here, is the precipitation, water falling from the atmosphere towards the land. And then we have the runoff over the land through the rivers, and this water then goes to the oceans. From the oceans, it evaporates back to the atmosphere and then again falls like, as a precipitation. So there are other major components of this water cycle. Just like we have that water which is going deep down in the land, which is referred as groundwater storage. And similarly, the water that's taken up by plants and used for their photosynthesis is called as a transpiration water. And the water that falls on the leaves, we call that as an interception part. So the question here rises is, why do we study this uh, water cycle as a whole, or the components of water cycle? So if anyone can answer me, I'd be glad to know.
Can you repeat the question, sir?
So why do we study this water cycle as a whole?
Because as we are humans, as well as we are protecting animals, we need water for our basic needs and
Yeah.
also for future
Yes.
generations.
Yes. So we just want to manage this water in a very good way so that we can sustain very easily on this earth. Yeah, that's the right answer. And we will get to know much more in the further slides. So
Can
the
you go to full mode, sir? Please.
yes,
Full mode screen.
I think this is full mode.
Is it, sir?
Yeah. So actually I have joined
Okay.
from this tab.
Okay, sir. No, no. We'll try from our side also. We will try to make it full screen.
Okay. Thank you.
Right, sir. Carry on, sir. Thank you.
Yeah. So there are different components of water cycle as I have explained earlier in the first slide only. So if I break down those components, so we have the atmospheric water, the water that's above in the atmosphere, the water that's on the surface of water, surface of earth, and the water that we have on the subsurface part. So if we go to the atmospheric water, we see the clouds. So clouds store the water and it falls as a precipitation. So if you look here, wait a second. So this is the precipitation part in the atmospheric part. And once it falls on the earth, so the amount of water that falls on the earth, some of it goes back to the atmosphere through the evaporation, and that we have here. And the water that's uh, stored or that falls on the leaves of plants or the trees, that we call as the interception part. And similarly, the water that's being used by the trees and goes back to the atmosphere is called as transpiration. So these four parts are defined as the atmospheric part of water. So in this course, mainly you will be going through the surface water, which is the title of the course. So it will be the overland flow, the water that is flowing on the land, and the surface or surface runoff, and the runoff that goes to the oceans. And similarly, the subsurface water is the water that goes deep inside the land. So it will first include the infiltration, the subsurface flow, and similarly, this infiltrated water goes to the groundwater recharge, and this flows as a groundwater flow, and then it goes back to the runoff. So particularly, you may have seen a diagram just like this. So here the water falls, it goes to the groundwater, then it goes horizontally towards the river that's here. So starting with the understanding of the hydrological system or the hydrological processes, one of the easiest way to go through is to define a system. So system is consists of group of the elements, which are the processes that are here: precipitation, evaporation, interception, and transpiration. So some of them acts as an input, some of them acts as a set storage, and some of them acts as an output. So if we look in this diagram, so this is a watershed. So these are actually the streams. So the water falls as a precipitation over this watershed and then it leaves through the stream. So there are other processes happening here which I have not shown. So this is how we define as an hydrological system, and we will try to see how we model them and try to understand each of the processes one by one. So
Sir,
yeah,
can I interrupt, sir?
yeah, yeah, yeah.
Sometimes interception. What will happens after interception? Will it go to as a operation or it will fall down on the ground?
So there are different things that can happen once the water falls as an interception. So it can evaporate or it can fall through the trees through and reach to the ground. So there are both things that could happen.
Okay, is it depends upon the leaf size or leaf
Yeah,
slope or something?
yeah, yeah. It will depend
Okay,
upon that because it's actually the water that's being falls on the leaves. So if the leaf size is high, so the water intercepted will be high and the evaporation will be high. The volume will be actually high, so it will be directly proportional to the leaf size.
okay, sir. Done.
So one of the important things in the hydrology we start with is the water budget after the water cycle. So water budget is you can understand it as an conservation of mass, what we have learned earlier in 11th and 12th grade. So water budget explains that the water that's coming towards the system and the amount of water that leaves the system. So the difference of this will be the change in storage. So neither you can create the water nor you can destroy the water in simple terms, if I say. So before that, why we do apply this water balance equation is the watershed. So watershed, we define it such land, which is defined as an area of land that if the water falls on that land and then it will be contributing towards a single outlet. So all the water that will be falling on the land, so it will just reach towards the common outlet. So then we can call this whole as a watershed. And using this water balance equation, we can just say that the change in storage happening over this water land will be the inflow minus the outflow. So let's say the inflow is around 10 meter cube and the outflow is 5 meter cube. Then the water that will be stored in this catchment will be around 5 meter cube, which is 10 minus 5. So the different processes happening towards this watershed. So we start with the precipitation. So precipitation will be the inlet to the watershed. And similarly, we have then the evaporation, which the water is leaving the system. Similarly, the transpiration, it's also the water leaving the system. So G in is the horizontal groundwater that's coming towards the region. So the water that's coming towards the watershed will be the precipitation, that's the inflow, and the groundwater. But this is the horizontal component of the groundwater. And similarly, we have the evaporation, that is the water leaving the system, transpiration, and similarly the groundwater that's going deep into the deeper layer, and the discharge. So I think everyone may have an idea of this water budget equation. We will have some questions on this ahead in the next few slides. So now the question is the storage term that we have seen in the above water balance equation. So we define the storage as input minus output. So the basic concept that Aru has earlier said in the first slide only is that we need to manage this water. And what happens in the water cycle is, let's say if there is some rainfall happening over the period of time, over the long 30 years, every year we see a particular rainfall, and some year there is no rainfall. So this is some kind of extreme. So that's not following what was actually happening. So we call these type of events as a hydroclimatic extremes. So they're defined as when there is a significant deviation from the long-term average. So let's say we take a simple example of the soil moisture. So this plot shows the soil moisture time series, and this red line shows the mean. So if we see that from this period to this period, the soil moisture has significantly decreased uh, over this period below the mean. So this decrease in the soil moisture has led to the drought events, as can be seen in the figure here. So we need to prepare for such type of climatic extremes that happen a couple of times or every year. Similarly, other type of climatic extreme is floods. Let's say we have the discharge. Rainfall happens in the monsoon, so there is a significant amount of precipitation happening over a land, and during that period, the discharge significantly increases above the mean, and this leads to the chances of high floods over this region. So these type of climatic extremes we need try to predict, understand, manage how we can deal with such type of events. You have any question here? How Arav?
Sir,
So you have any question here?
the question is related with the floods.
Yeah,
Uh, is the floods are occurring only in urban area or rural also?
yeah. So I
That's the
think
question because yes, sir.
yes. So the case of the floods, it will first depend upon the precipitation. Let's say a region receives high amount of precipitation, so there is high chances of having floods. But if you compare between the rural and urban, so let's say there is a fixed amount of precipitation happening over both the regions. So now the question is, where are the chances of high floods? So it will be the urban because of constructions. So there will be very less infiltration happening over the urban region. So that amount
Yes,
of
sir.
water will flow ultimately towards the stream, and it may cause more floods in case of the urban cities.
Is the runoff quotient can be increased by any research means in urban area?
Yeah, I think they try to dig some wells in the urban areas so that the water flows over those holes or something. But from my point, what I have know, it's very difficult because the pavement is done everywhere. You do the concreting everywhere, so less amount of water goes down into the earth or the surface, and then every water comes ultimately towards the outlet. So there are high chances in the urban, and to stop that, it's I think difficult, but it can be done.
Okay, sir, fine. And what is the y-axis units in other droughts, sir? Soil moisture, it's a
Soil
percentage.
moisture, usually we measure it in terms of depth. So let's say in
Okay, depth.
mm. Yeah.
Okay,
So there
okay.
are different units you can use for the soil moisture. Also, few of them use as a meter cube.
Okay, fine, sir.
So the question is, what can be done if, let's say, we understand that, for example, a whole water cycle, and we know now these hydroclimatic extremes can occur. So what can be done uh, to save the community from these extremes? So the first point is to be improve our monitoring system and the early warning system. So let's say every day you wake up, you listen to the news, and you hear that tomorrow it's going to be high rainfall. So there is some uncertainty associated with that prediction. Let's say 50% chances that rainfall is going to happen, 70% chances are that rainfall is going to happen. So first we have to modify that system. We have to get more accurate, and we have to improve that monitoring system. So this is actually depends upon the models that we have through which we predict and also the data we use. And I think more focus will be to on the uh, obtaining the high resolution data and then do the forecasting at different levels. For example, you receive the warning before 1 month. So that will be more better because we get a more time to manage the things. Second is to plan for extremes. Let's say we have an area where every time that rainfall falls between the monsoon, but we don't need to prepare for that monsoon. We need to prepare, let's say, if there is no rainfall during that monsoon period, what can be done? Let's say we built dams, we try to store water. So that things have to be done. We have to plan for such type of extremes. And the third thing will be to strengthen land water management. So how to sustainably use the groundwater and how we can do the watershed based planning. Watershed based planning, the rainwater harvesting and other things. So I would like to further discuss this groundwater issue. So anyone who has idea where in India groundwater is mainly extracted, region, which region? So anyone who knows this?
Is it a geological region or you are comparing urban and rural areas?
No, no, it's just for example, you take the states, which of the state use most of the groundwater.
Okay, probably in desert areas or so.
Yeah, but the desert area, if you go to the Rajasthan and Gujarat, it's particularly the Rajasthan, the desert area that you have, there is no such type of vegetation, so they don't use the groundwater for the vegetation. So
Punjab,
for
Haryana.
yeah, Haryana and Punjab, it's these two regions which use highly this groundwater for the irrigation purpose, and it has been seen from last couple of decades that the groundwater depth is increasing if you measure it from the top of the surface. So the groundwater is almost diminishing in their areas.
What is the depth, sir, in these two areas of average depth?
Yeah, yeah.
What is the average depth of extraction in these Punjab, Haryana, and other?
I don't remember the exact depth, but it's very extensively
Okay, that is
being, yeah,
relatively high.
yeah, it's
Uh-huh.
relatively
Okay,
very high.
okay,
If you take this Indo-Gangetic plan, these regions highly use this irrigation, groundwater used for irrigation. So one is if you use the groundwater for drinking, so it won't be much as compared to when you use it for the irrigation purpose to irrigate the land.
okay.
So yeah, one question here is, let's say for example, you have the precipitation, you know almost every component of the water cycle. So which of the part of the water cycle takes longer time? Let's say for example, in precipitation happens first day, then after 3 4 days you have again the precipitation. Let's say there is a decrease in the groundwater, you extract the groundwater by around 30 meter cube. So in order to refill that groundwater, so it will be going take longer period of time because it's a very slowest process in the hydrological cycle. So that's why we need to understand it very well and use it very well so that it won't create much problems in the future. So yeah, this slide I have kept blank, but yeah, I will just bit explain about the measurements. So anyone having an idea of how easy or how difficult is to measure these hydrological variables? So let's say, for example, you know the precipitation. So the precipitation is measured. You just use there are different ways you can measure the precipitation. For example, at a particular location, you use a floating point rain gauge station. Usually we have the rain gauge stations in India. So let's say this is some bucket type which have marks on it and it's kept at some place. and the rainfall falls over this region, over this bucket, and it gets filled, and we measure this depth, and this depth is reported as the amount of rainfall that we have. So this is one way of measuring the precipitation. So similarly, we have, let's say, for example, soil moisture. In the soil moisture, let's say, the one of the common examples that we have is that we take the sample from the earth, and then we dry it down. We note down the mass before and after drying, what's the mass. So let's say this is M1, this is M2, and we compare this M1 minus M2. This is the amount of water that's stored in this, and it's represented as the soil moisture. And similarly, we have, let's say, for example, the stream flow. You have staff gauges and other things. Let's say this is a river flowing, and we have the staff gauge here, and we try to measure the depth of water here through this scale. So the common issues we have is that, let's say, for example, this is a watershed. Like, watershed is an area that we have already defined. And here, let's say we have the buildings. Now here we have some agriculture, and here we have trees or the forests, we can say. So the usual practice is that, let's say we take here one sample, here one sample. Let's say we measure the rainfall or the soil moisture, and we take here the soil moisture. So this will be the soil moisture 1, soil moisture 2 sample, and soil moisture 3 sample. So the question is, the soil moisture that we have here, does this one, or this one represent the soil moisture of this location? Can it
Sir?
represent? So let's say we measure the soil moisture here, here, and here. So can these three represent the soil moisture of this location?
Location means the boundary, the
Yeah,
entire boundary
area,
you're asking.
area. You can say the area.
What is the measurements you have taken in meter square or kilometer square, or what is the units of
Soil
catchment?
moisture is usually measured as meter cube per meter cube.
No, 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 sir. No, no, not that my question. Whatever you have boundary line you have drawn,
Yeah, yeah.
that area, catchment area is
It's a very big, you can uh,
okay. It's
take it as
very
a very
big.
big catchment, so that it includes the urbanization also. It takes
Okay.
as the cropland also, and the forests are also included in.
Yeah, since the soil is normally heterogeneous, it is going to represent only a particular area,
Yeah,
particular
so
point.
yeah, so the problem is actually the spatial heterogeneity that you are mentioning. So all the measurements that we are making, so spatially it's very difficult. So because the surface is very heterogeneous. So to overcome these, for example, we have some other methods just like satellite methods. So now using the satellites, these hydrological variables are being estimated. But the question again in the satellite method is also they try to normalize this spatial heterogeneity. So measurements part in the hydrology is quite bit difficult. Accurate measurement is very difficult, and these measurements influence the prediction that we do in the hydrology. So before
And
going to the problems, I think I will restart the meeting. So it has been already 40 minutes. So there is a limit on this. Can you rejoin again?
yeah, yes, sir.
Yeah, thank you.
Sir, what is that soil moisture topic? What is the soil you are considering?
Soil, you can take any. I'm just giving an example of how actually it's difficult to measure this hydrological variables. And if you measure at a particular location, it does not represent the whole area. It will just represent that location only. It can be any types of the soil. It's just I am giving an example.
Okay, sir.
Yeah. So please rejoin again. I will just restart the meeting.
Fine, sir.
So good afternoon. Welcome back, everyone. We will start with the problem one, which is considering a watershed of area 500 kilometers square that receives an annual rainfall of 100 mm, and it's to be assumed that 30% of it is lost evapotranspiration and 20% of it infiltrates into the groundwater, with the remaining contributing to the runoff. So what we are asked to do in this question is to first compute the runoff volume into kilometer cube and then classify rainfall runoff and evapotranspiration as input, output, or storage. So area is 500 kilometers square and the rainfall is 100 mm. So the evapotranspiration, it's 30% of rainfall, which is 30% of 100 mm, which is equal to 30 mm. And similarly, we can compute infiltration, which is as 20% of rainfall. So it can be 20% of 100 mm, which is 20 mm. So total precipitation is decomposed into three parts. One is the evapotranspiration, second is infiltration to groundwater, and the third one is runoff. Total precipitation is 80 plus infiltration to groundwater plus runoff. So it's given that rainfall is 100 mm, ET is 50 mm as we have computed here. Sorry, it's 30 mm. And similarly, this is 20 mm. And now we are going to compute the runoff. So the runoff will be 100 minus 30 minus 20 mm, which will be equal to 50 mm. However, it's asked to compute the volume in kilometer cube. So therefore, runoff in kilometer cube will be equal to runoff in mm into the area of catchment. This will be equal to 50 mm into the area of catchment, which is 100 kilometers square. So we can convert this mm into kilometer, which 10 is power minus 6 kilometer into 500 kilometers square. So this will be 25 into 10 is power minus 3 kilometer cube, or you can write it as 0.025 kilometer cube. So hope this one is clear, this problem. Anyone having problem in this question? So the problem two is that we are given an equation of the flow of water through a river by a differential equation where Q is denoting a flow, I is denoting rainfall. At time t is equal to 0, it's given that the discharge is Q naught. So we need to first solve this differential equation and then compute the Q of t for different days and then plot the results over 20 days. So the first interesting thing is in this question is that this differential equation is given for a rainless period. So when it's given rainless period, therefore I of t will be equal to 0. And the differential equation can be written as k k dq by dt plus q of t is equal to 0 as I of t is equal to 0. Therefore, dq by q will be equal to minus 1 by k of dt. We need to solve this differential equation by integrating both sides. So this will be log of q of t minus t by k plus constant of integration. At t is equal to 0, q of t is given as q naught. Therefore, so this will be becoming as log of q naught equal to c. So we can replace this value in the above equation and we will get as log of q of t is equal to minus t by k plus log of q naught. So solving it will be log of q of t minus log of q naught equal to minus t by k. This will be log m minus m, which is equal to log of m by n. So q of t can be written as q naught e raised power minus t by k. Now the question asked is to plot q of t for different times, and we'll see how it varies with time. So at time t is equal to 0, in this equation we can plug the values. Q of t will be q naught e raised power 0, which is equal to q naught. Let's say this is q naught. And similarly, if you increase t, so this constant e raised power minus t by k, so what will happen to this constant? Yeah. So this will q of t will start decreasing as as t increases exponentially. Yeah. So this will go like this, and let's see if it becomes 0. So for 0 discharge, this will be q naught e raised power minus t by k. Since q naught is some constant, then e raised power minus t by k is equal to 0. This is only possible when t tends to infinity. So this discharge will be asymptotic to x-axis and will not touch exactly, but will be asymptotic to the x-axis at x is equal to 0. Sorry, y is equal to 0. So is there any doubt in this problem? So let's switch to the problem number 3. This is similar to the problem number 2, but here we are given that precipitation will be remaining 1 for t equal to greater than 0, and q of t will be 0 for t is equal to 0. Similarly, we need to solve the differential equation and plot I and q for different values of time. So we can start with the problem. So this will be dq by dt plus q is equal to I. I is given is 1 unit. So dq by dt plus q is equal to 1. So we can write it as dq by dt is equal to 1 minus q, and dq upon 1 by q is equal to 1 by k dt. We integrate both sides again, similar to what we have done in the previous problem. This will be log of 1 minus q equal to t by k minus times. So this will be log of 1 minus theta is equal to minus t by k. Sorry, plus constant of integration will be here. Now we are given at t is equal to 0, q will be 0. So if we use these values in above equation, we will get log of 1 is equal to c, which is, you can put back the value of c here. This is going to be 0. So this will be log of 1 minus theta equal to minus t by k. And 1 minus theta will be e raised power minus t by k. So if we further solve this, so theta as a function of time will be 1 minus e raised power minus t by k. So if you recall in the previous one problem, so discharge came out to be e raised power minus t by k. Here it's a bit different. It's 1 times minus e raised power minus t by k. Now the question is asked that you need to plot rainfall over time and q over time. So what actually is happening is, let's say first we plot the rainfall, which is I of t as a time t. So this will be constant of 1 unit that occurs over this period. This is given for t equal to greater than 0. I of t always remains 1. And now we are going to plot q of t. So at t is equal to 0, we know the value of q is equal to 0. So it will start from here. But as you increase the t, so e raised power minus t by k, so it will tend to decrease. And the quantity q of t, which is 1 minus e raised power minus t by k, this will also start increasing. And if we look into this quantity, I will just show here. Let's say t tends to infinity. T is increasing and increasing, and this quantity will become 0. And the q of t will be tending to 1. So the moment at this point, the rainfall that's happening over the watershed is getting converted into the whole runoff. So if we plot this, so this will be just like this. And this is going to be 1 unit. So here the discharge curve becomes asymptotic to y is equal to 1. It will be touching this at infinity. So it's a bit different as what we saw in the previous problem. If you recall that in the previous problem, we saw that the discharge was decreasing from Q naught, let's say, and it was touching the x-axis at x is equal to infinity. So any doubts in this problem also? You can please. So coming to problem number 4. So this was the question asked in the gate in 2015. So the question goes, the average surface area of a reservoir in the month of June is 20 kilometers square. And in the same month, the average rate of inflow is 10 meter cube per second. The outflow is 15 meter cube per second. The monthly rainfall is 10 centimeter. We have a seepage loss of 1.8 centimeter. The change in storage is 16 million meter cube. And we need to compute the evaporation in centimeter. So this problem is related to the water balance, which is change in storage is inflow minus outflow. So if we look into the problem, the first thing we can do is to convert all fluxes that we have here into the centimeter. So let's say we have inflow, which is 10 meter cube per second. This can be computed as, if we need to convert it into the centimeter, we will first divide it by the area, which is 20 kilometers square, and multiply by the time, which is 1 month, will be 30 into 24 into 60 into 60. Kilometer square can be written as 10 feet to the power 6 meter square. And after the computation of this, you get a value of 129.6 centimeter. And similarly, if we compute the outflow, which is 15 meter cube per second, so it will be 15 divided by the area, which is 20 kilometers square, into the time, which is 30 into 24 into 60 into 60. The value will be approximately equal to 194.4 centimeter. Now, if we try to check here, the storage is given in meter cube. Storage is given as 16 million meter cube. So we'll also convert this into the centimeter. We will divide it by the area, which is 20 kilometers square. So this will be 16 into 10 to the power 6, 20 into 10 to the power 6. This will be also meter square. Now this will be meter cube. This will be 0.8 meter. And if you convert it into the centimeter, this will be 80 centimeter. Now, if you write the water balance equation, this will be, let's consider a catchment. This is inflow is precipitation. And then we have the another inflow. We have the outflow. We have the seepage loss. We will be having evaporation. And also, and this is these are the values, and the change in storage is given as, now it is 680 centimeter. So if we write the equation, it will be precipitation plus inflow minus the evaporation plus the seepage loss plus the outflow. So interesting thing in this problem is that this change in storage is not given, that whether it's positive or negative. So it means that either the storage have increased also, or it could be also decreased also. So either it's plus 80 or it's minus 80. So if we solve for plus 80, so this will be 80 equal to, you plug the values of precipitation, which is 10 centimeter, and then we have inflow that we computed into the centimeter, which is 129.6 centimeter. minus the evaporation minus the seepage loss. Seepage loss is given as 1.8 centimeter plus the outflow, which is 194.4 centimeter. So if we solve E, it will be coming around minus 136.6 centimeter. So this is not possible that having evaporation as negative. So thus plus 80 change in storage is not possible. So we now solve also for minus 80. If plug the values, it will be minus 80 equal to 10 plus 129.6 minus E plus 1.8 plus 194.4. And in this case, evaporation will be coming out to be at 23.6 centimeter. So which is your D option. So the change in storage is actually negative. This water level has decreased, and this is due to the excessive evaporation that we are having, which is coming out to be 23.4 plus the seepage loss and plus the output. So any questions in this problem? So if not, I will stop the meeting and we will meet next week with a new tutorial. Thank you, everyone.